Imagine a continuous sealed infrastructure corridor subjected to a relentless hydrostatic pressure of 20 atmospheres, operating 24 hours a day, 7 days a week, at a depth of 200 meters below the ocean surface. This is not a static storage facility, it is a 150-kilometer-long active kinetic transport artery. The engineering challenge is not merely holding back millions of tons of seawater. The true complexity lies in maintaining a near-absolute internal vacuum of 0.01 atmospheres while simultaneously propelling a magnetic levitation payload at 1,000 kilometers per hour. How does modern heavy engineering construct a submerged vacuum tube capable of withstanding these diametrically opposed pressure differentials without facing catastrophic structural implosion? To understand the sheer physical scale of this megaproject, we must first analyze the primary manufacturing nexus. The construction does not begin at sea, but at a specialized purpose-built coastal fabrication facility spanning exactly 500 hectares. This megasite operates as an independent industrial ecosystem. It is equipped with a dedicated heavy-duty internal rail network designed to transport raw materials, thousands of tons of aggregate, specialized Portland cement, and metallurgical-grade steel directly to 4 parallel dry docks. These dry docks operate simultaneously, functioning as the primary casting basins for the tunnel segments. The core objective of this facility is to mass-produce the individual modules that will form a continuous 12-meter diameter underwater tube. The operational principle of the transport system within this tube relies on the complete elimination of aerodynamic drag. In standard atmospheric conditions, a vehicle traveling at 1,000 kilometers per hour would encounter thermal barriers and air resistance so severe that the energy required to maintain velocity would be economically unviable. Furthermore, the thermodynamic heat generated by surface friction would lead to mechanical failure. By utilizing an array of industrial-grade, multi-stage rotary vane and turbomolecular vacuum pumps distributed along the projected route, the internal atmosphere is mechanically evacuated down to a pressure of 0.01 atmospheres. Within this artificially sustained near-vacuum environment, the magnetic levitation train can achieve its cruising velocity using solely electromagnetic propulsion, completely bypassing the thermodynamic limitations of traditional atmospheric transit. The fundamental building block of this megaproject is the individual tunnel module. Each unit is an engineering behemoth measuring precisely 200 meters in length and displacing approximately 50,000 metric tons of water. The fabrication of a single module involves a highly calibrated, multi-layered material science approach. The primary load-bearing core is constructed from ultra-high-strength marine-grade reinforced concrete. This is not standard construction material. It requires a precisely calculated water-to-cement ratio, alongside the integration of silica fume and fly ash to minimize porosity and prevent chloride ion penetration from the surrounding seawater. The internal steel reinforcement matrix is woven with strict dimensional tolerances, utilizing epoxy-coated rebars to provide maximum tensile strength against the longitudinal bending moments the module will experience during the towing and immersion phases. The curing process of this 50,000-ton concrete core presents a massive thermodynamic challenge. The hydration of cement is a highly exothermic reaction. In a structural pour of this magnitude, the internal heat generated can easily exceed 70 degrees Celsius. If the temperature differential between the core and the exterior surface surpasses 20 degrees Celsius, thermal cracking becomes inevitable, severely compromising the structural integrity and water tightness of the module. To mitigate this critical risk, the engineering team embeds an intricate network of specialized cooling pipes directly into the rebar matrix. Millions of gallons of chilled water are continuously circulated through these pipes during the 28-day curing cycle. This is strictly regulated by an automated thermal management system that monitors internal temperatures via thousands of embedded thermocouples. Surrounding this massive concrete core is the project's most critical defense mechanism, a double-walled exterior shell engineered from a specialized titanium steel superalloy. This metallurgical composite is specifically designed to resist both the extreme corrosive properties of the saline environment and the immense crushing force of the hydrostatic pressure at depth. The outer titanium layer acts as an absolute barrier against galvanic corrosion, while the inner steel substrate provides the necessary ductility and yield strength. The assembly of this metallic exoskeleton introduces a secondary layer of manufacturing complexity. Due to the massive scale of the steel and titanium plates, traditional manual welding is structurally insufficient and unacceptably slow. Therefore, the megasite employs a synchronized battalion of fully automated industrial robotic arms. These robotic units operate on a 6-axis mobility platform, guided by real-time, laser profiling scanners. These sensors map the exact topography of the metal joints milliseconds before the tool makes contact. They execute friction, stir welding across the entirety of the module's exterior. Unlike conventional arc welding, friction stir welding uses a rotating tool to generate frictional heat, plasticizing the metal and mechanically forging the two plates together without reaching their melting point. This solid-state joining process produces a continuous, seamless bond with a microscopic assembly tolerance of less than 0.1 millimeters. To monitor the health of the structure post-assembly, a dense fiber-optic acoustic emission sensor network is embedded directly between the titanium shell and the concrete core. This active monitoring system is capable of detecting microfractures, material fatigue, or minute shifts in stress distribution in real time, transmitting gigabytes of structural data back to the central control matrix every single second. Once the automated fabrication sequence and structural curing process are completed, the massive dry docks are flooded with seawater. The transition from a static land-based construction environment to an active dynamic maritime deployment phase introduces a monumental logistical challenge. We are now dealing with the transportation of a 50,000 metric ton concrete and titanium monolith out into the open ocean. This operation requires a highly synchronized fleet of specialized marine assets. A designated towing armada consisting of 8 highly maneuverable azimuthal tugboats, each generating precisely 15,000 brake horsepower, is physically attached to the tunnel module via high-tensile steel towing hawsers. The towing operation is not a simple matter of mechanical drag and pull. The marine engineering team must continuously calculate the dynamic fluid resistance, factoring in localized surface winds, unpredictable swell patterns, and subsurface ocean currents. The tunnel module is engineered to be positively buoyant by a strictly controlled and narrow margin, leaving only a few meters of freeboard visible above the waterline. Navigation requires uninterrupted real-time meteorological data feeds and continuous tension monitoring on the towing cables. This prevents asymmetric loading, which could induce severe structural torsion and critically compromise the titanium exterior shell before the module even reaches the installation zone. Upon arriving at the designated marine coordinates, the module is transferred to the control of massive twin-hulled jack-up barges, which function as a stabilized floating command center. This handover marks the commencement of the most critical engineering maneuver in the entire sequence, the immersion process. The margin for error during this phase is effectively zero. Lowering a 200-meter-long, 50,000-ton structure through a water column of 200 meters requires extreme mechanical precision and environmental control. The descent is initiated by carefully pumping seawater into a series of internal ballast tanks integrated within the module's structure. This controlled flooding gradually shifts the monolith from positive to negative buoyancy. To maintain absolute horizontal alignment and structural stability during the descent, a computerized winch system located on the jack-up barges coordinates a complex network of heavy-duty counterweight cables. These automated winches make micro-adjustments in real time, responding instantly to telemetry data from internal gyroscopes and external water current sensors. As the module approaches the seabed trench, which has been previously excavated and precisely leveled with a specialized gravel foundation bed, standard satellite GPS tracking becomes entirely ineffective due to water attenuation. The installation engineers must rely entirely on an ultra-high-frequency acoustic positioning system. Transponders mounted on the descending module ping receiver arrays installed on the previously laid tunnel sections. This acoustic triangulation allows the command center to calculate the precise X, Y, and Z coordinates, guiding the massive concrete block into its final alignment with a mechanical locking tolerance of less than 2 centimeters. The mechanical connection between two modules at a depth of 200 meters is an unforgiving procedure governed by the laws of fluid dynamics. The primary waterproof seal is achieved using a massive, highly engineered elastomeric component known as a GINA gasket. This specialized rubber profile is firmly mounted on the front face of the descending module. As the mechanical hydraulic pulling rams engage and slowly draw the two modules together, the initial contact compresses the GINA gasket, creating a preliminary seal. Once this primary seal is established, the seawater trapped in the small isolation chamber between the temporary steel bulkheads of the two modules is forcefully evacuated using heavy-duty submersible pumps. The rapid removal of this water creates a localized area of lower atmospheric pressure within the joint. Instantly, the overwhelming hydrostatic pressure of the surrounding ocean, measuring 20 atmospheres, pressing inward, forces the new module tightly against the existing tunnel structure. This immense natural water pressure permanently compresses the GINA gasket to its final design specification, creating an absolute watertight seal. However, before the internal steel bulkheads can be removed and the internal space safely integrated into the main tunnel, the newly formed joint must undergo rigorous diagnostic testing. Specialized robotic ultrasonic and X-ray scanners are deployed within the bulkhead space to thoroughly scan the entire circumference of the compressed GINA gasket. These sensors are searching for microscopic air pockets,
elastomeric deformations, or structural anomalies.
The joint is then subjected to a stringent stress test, artificially simulating localized pressure spikes and high-velocity current impacts. Only when the computerized diagnostic system confirms absolute structural integrity and zero water ingress is the joint officially certified, allowing the vacuum pumping phase to commence. The successful mechanical sealing of the final abyssal joint initiates the most power-intensive phase of the entire megaproject, the macro depressurization sequence, transforming a 150-kilometer-long, 12-meter diameter subterranean cylinder from standard atmospheric pressure down to a sustained operational vacuum of 0.01 atmospheres is an unprecedented thermodynamic undertaking. This is not a static vacuum chamber, it is a dynamic hyperscale kinetic corridor. To achieve this near-vacuum state, the engineering matrix relies on a distributed network of thousands of multi-stage roots blowers and turbomolecular pumps, structurally integrated into dedicated ventilation shafts, extending from the surface down to the seabed trench. When the central command grid activates the primary extraction sequence, these industrial-grade pumps must evacuate millions of cubic meters of atmospheric gases. The process must be strictly regulated to prevent sudden adiabatic cooling inside the tube, which could induce severe thermal shock to the inner steel lining. Furthermore, the system must continuously counteract material outgassing, the slow release of trapped gases from the concrete and metal surfaces, by maintaining a continuous, automated extraction cycle, 24 hours a day, 7 days a week. Operating within this artificially sustained low-drag environment is the core kinetic payload, the magnetic levitation transit system, stripped of the aerodynamic resistance that dictates the physical limits of conventional high-speed rail and aviation. The internal transit pods utilize a proprietary linear synchronous motor propulsion array. The tracks laid along the interior invert of the tunnel are embedded with thousands of electromagnets to generate the necessary levitation and propulsion forces without melting the internal circuitry. Due to electrical resistance, the transit pods are equipped with advanced superconducting magnets cooled by a closed-loop cryogenic liquid helium system, maintaining a functional temperature near absolute zero. The continuous interaction between these supercooled magnetic arrays and the active track stators propels the 400-ton transit modules to a sustained cruising velocity of 1,000 km per hour. At this extreme velocity, traditional friction-based braking systems are entirely obsolete. Deceleration is achieved entirely through regenerative electromagnetic braking, converting the immense kinetic energy of the moving pod back into electrical current, which is then fed directly back into the primary power grid of the tunnel infrastructure. This closed-loop energy recovery system significantly optimizes the overall electrical consumption profile of the Megaproject. However, operating a high-velocity transit system within a submerged vacuum tube requires an absolute fail-safe approach to emergency management. The engineering solution to a potential hull breach or localized pressure loss is a highly automated system of titanium isolation bulkheads distributed every 5 kilometers along the entire 150-kilometer route. These massive, multi-ton blast doors remain recessed within the tunnel walls during normal operations. In the event of a critical pressure anomaly detected by the fiber optic acoustic emission sensor network, the command matrix can deploy these bulkheads via redundant hydraulic accumulators in less than 3 seconds. This instantaneous compartmentalization isolates the compromised sector, preserving the vacuum integrity of the remaining tunnel network and securing the structural safety of the active transit pods. Furthermore, each isolated segment is equipped with independent, pressurized emergency egress pods, capable of vertically ascending to the ocean's surface, guided by acoustic beacons, ensuring a standardized industrial-grade evacuation protocol, regardless of the external hydrostatic conditions. Beyond the immediate mechanical triumphs, the completion of this abyssal vacuum corridor represents a fundamental paradigm shift in global macroeconomic infrastructure. By reducing an intercontinental logistics route that traditionally requires 10 hours of high-altitude aviation down to a frictionless, 45-minute subsurface transit, this megaproject completely redefines the parameters of high-speed freight and passenger transport. The economic impact extends far beyond the operational revenue of the tunnel itself. The sheer scale of construction acts as a massive industrial engine, forcibly accelerating the production capacities of the global supply chain. The demand for the specialized titanium steel superalloy utilized in the double-walled exterior shell alone required a complete overhaul of international metallurgical output capabilities. Foundries and heavy forging facilities were forced to upgrade their automated production lines to meet the unprecedented volume and microscopic tolerance requirements of the project. Similarly, the aerospace and industrial machinery sectors experienced a massive injection of capital and research to design, test, and manufacture the hyperscale turbomolecular vacuum pumps and cryogenic cooling systems required to sustain the internal environment. This project did not merely purchase existing technology, it mandated the invention and mass production of next-generation industrial hardware. In conclusion, the successful deployment and operation of this submerged vacuum transit corridor stands as the ultimate empirical proof of modern engineering's capacity to subjugate extreme physical environments. It demonstrates an unparalleled mastery over hydrodynamics, thermodynamics, and material science. By successfully balancing the crushing external force of millions of tons of seawater against the internal void of an artificial vacuum, humanity has effectively rewritten the structural limits of global infrastructure. If you want to understand the mechanical reality behind the world's most complex industrial structures and heavy engineering achievements, make sure to subscribe to the channel and turn on notifications. We break down the physics, the machinery, and the logistics that build our modern world.